We now continue our discussion on the variation of parameters method for finding the particular integral by taking another example which we have put up on the board. So the equation runs, this is, as we mentioned earlier, this is variation of parameters to solve this. Equation is y double dashed plus 4y is equal to sine 2x, which indeed is another way of writing d2y dx2 plus 4y is sine 2x. And another alternative way of writing is d square plus 4 into y is sine 2x. So as we have done before, the first step is to find the complementary function, which we will do, and we will do it a little fast this time, not going into all the details, because the processes are now familiar to us. So we just straight away write that the auxiliary equation is m square plus 4 is equal to 0, and the roots are plus minus 2i. So the complementary function yc is c1 cos 2x plus c2 sin 2x. We look for a particular integral. According to the variation of parameters, we will replace c1 by a function u, c2 by a function u, both are functions of x, and get the replacing c1 by u and c2 by v. This u is actually ux and v is actually vx. What we get is, after replacement, we will get y, particular equation, particular solution is u. We label this as y1 and we label this as y2. So u cos 2x plus v sine 2x. And we proceed to find u and v by the formulas already given. We'll do that work. We recall that u is given by minus integral y2. This was y1 and this was y2. So minus y2, that is sine 2x, into capital X, which is also sine 2x, over Wronskian dx. Here the Wronskian is, in this case, w is nothing but determinant cos 2x sin 2x y1 y2 cos 2x sin 2x, and derivative of this, this is minus 2 sin 2x and this is 2 cos 2x. When we evaluate this, it becomes cos squared 2x into 2 plus sine squared 2x into 2. So this is 2 cos squared 2x plus sine squared 2x, and happily that is equal to 2 into 1. So the value of the Wronskian is equal to 2 in this particular case. We capture that and rub out all that work. So the value of u is nothing sine squared 2x divided by 2 with the minus sign. This is minus half integral. Sine square theta is half of 1 minus cos 2 theta. Sine square theta is half of 1 minus cos 2 theta. With these two out, we'll have to put another half 1 minus cos 4x dx. This gets clubbed here. So this is minus 1 by 4 integral 1 minus cos 4x dx. This is minus 1 by 4. The integral of 1 is x minus cos 4x. Minus cos 4x will integrate to sine 4x over 4. So our u is minus 1 by 4 x plus sine 4x by 4. We'll capture it up here. U is minus 1 by 4 x plus sine 4x divided by 4. We now get the value of v. In like fashion, the value of v is y1 capital X Wronskian dx, that is equal to y1 is cos 2x, so integral cos 2x, x is sine 2x, Wronskian is 2 dx. Now this is cos x, cos theta, sine theta type. It is half of sine 2 theta, so one can write this as 1/4 of sine 4x, and that is nothing but minus 1 by 16 cos 4x, because sine 4x will integrate to minus cos 4x over 4. This 4 with this will give you minus 1 by 16 cos 4x as the value of v, which we will write down here. V is equal to minus 1 by 16 cos 4x. So, if we substitute these values of u and v in the solution, particular integral is u cos 2x plus v sin 2x with this value of u and this value of v, then that becomes the particular solution of the given differential equation. So that is the second example, and both these examples together give us a little familiarity with the method of variation of parameters. That's all. We now visit the very important equation which is called the Cauchy Euler or the Euler-Cauchy equation. Now, here the form of the equation is one that is called a linear second order, because the highest derivative is again second order. That means this is d2y dx2 plus a1x dy dx plus a2y is a function of x. So we have taken the complete equation in which the right hand side is not 0 but a function of x. So the equation is Number one, it does not have constant coefficients. It's not a second order equation with constant coefficients, but has an x squared term, an x term, and on the right hand side we have a function of x. So this is an inhomogeneous equation. This is the most general form, but the target is how a simple substitution can convert this equation to a second order equation with constant coefficients, which is easier to handle. So we will see the substitution and we will see how to convert the given equation, which is not with constant coefficients but with variable coefficients, functions of x, and we will see the substitution. We write the equation once again on top and see what is the substitution that converts the equation to the target equation is second order linear equation with constant coefficients. So we put the equation once again on top. The original equation is x square y double prime a1 x y prime plus a2 y is a function of x. We can use the d operator to denote this equation in a slightly different way. In fact, the d operator allows us to write this as x square d2 y plus a1 x dy plus a2 y is a function of x. In other words, this can be condensed to x square d square plus a1 dy a1 xd a1 xd plus a2 applied on y is function of x, where x square d2 operated on y means x square second derivative of y plus a1 times x into first derivative of y plus a2 simply multiplied by y is equal to x, function of x. That was the original equation. So these two are identical, this equation here and this equation here, they are identical, excepting that this is used, this is written using the symbolic d operator form. Now we'll effect the substitutions. We have to remind ourselves that when we write y double dash, it is d2y dx2, and when we write y prime, that represents dy dx. Substitution. That converts the equation to a linear second order equation with constant coefficients is very simple. x is equal to e to the power of z. In other words, this also implies that z is equal to log base e x. Once we do that, let us find out what are the expressions for dy dx and d2 by dx2. We'll do it one by one. Now, x is equal to e to the power of z. This implies dy dx is equal to d dx of e to the power of z. That is equal to d dz of e to the power of z into dz dx. So dy dx is d dx of y, d dx of y, d dz of y into dz dx. Yeah, now it looks fine. Dy dx is d dx of y, is d dz of y, dz dx. This is the chain rule. That means this is equal to dy dz. And what is dz dx? From here, one can see that dz dx is nothing but 1 over x. So this is equal to, from here, it is equal to this into 1 by x. So if you cross multiply, we get x times dy dx is dy dz. So this is one important result which we need to capture. We'll hold it. X dy dx is dy dz. We'll write it in one corner and proceed further from there. So x dy dx is equal to dz dx. Rub out the entire thing from here. Starting from there, x dy dx is dz dx. We differentiate once again with respect to x, both sides. So d dx x dy dx is equal to d dx of dz dx. That's fine. We'll do the left hand side and the right hand side separately. On the right hand side, we can write that this is d dz of dz dx dz dx into dz dx. If we differentiate this once, we get, on the right hand side we are differentiating with respect to x. So d dx of x dy dx is equal to d dx of dy dz, that is d dz of dy dz, okay, this is d dz, fine, into dz dx. Now that is on the right hand side nothing but d2y dz2 into dz dx, which is 1 by x. We'll capture this here. Left hand side, first is keep this constant and differentiate this. So x d2y dx2 plus keep dy dx as it is and differentiate x. So these two are equal. Now if we multiply throughout by x, because there is a denominator x here, we will convert these to the following, that x square d2y dx2 plus x dy dx is equal to d2y dz2. In other words, we can write this is dy dz, x dy dx is equal to dz dx. Fine. So we change this equation as follows. We write it in a different way. X square d2y dx2 is d2y dz2 minus x dy dx. So this from here is implied x square d2y dx2 is equal to d2y dz2 minus x dy dx, and that is equal to d2y dz2 minus x dy dx is equal to dy dz. এবার পুরো ঘেবড়ে গেছে মালটা, হয়নি, বুঝলে? আচ্ছা থাক।